chapter 16, solubility, last equilibrium chapter. James, what is the problem? Okay, today I have mostly just example problems for you. We talked about, and I had to read about solubility and KSP and saturated and that kind of thing. We're going to spend most of our time just trying to work through some problems and seeing different ways questions can be asked in this chapter. I'll be able to, at the end of the hour, start talking about just some variations on these things. You should be able to get into the 50s in the homework tonight, into the 50s. And then over the next day or so, we'll be able to go much farther. But yeah, we're taking this kind of slow, fortunately, because even though, as I've told you, it is just another general equilibrium chapter, it still does have its own little context, and so we have to kind of get the feel for that. So I don't want to rush through it. What's that?
Just more vectors. It's actually really easy. You only have 13 questions.
Just based on what we did before. Okay. And then, yeah, you'll be able to do much more today. And I hope you do. So we're going to record for Nick today, our friend Nick.
Damn. I was trying to show the thing.
Okay, here we go. Prakya, you ready?
Yes.
All right, let's go for it. This video is dedicated to you, Nick Watson. And we just sent you a text to let you know that it was going to be done, so don't forget to watch. And if you're not watching, then you'll never know that we sent it. We begin with this one. I'm going to ask you to just go through this one with me. Let's talk about it, get the hang of what these questions ask. And then for a couple more, I'll ask you to try some. You'll want to have a calculator out.
I'm using your calculator. Go ahead.
Oh. So use the following data to calculate KSP value for this solid. The solubility of CaC2O4 is 4.8 times 10 to the negative fifth. For these problems, if you're in doubt, if you don't really know what to do with the information given to you, try to make an ice table. If you're in doubt, try to make an ice table. Now, there are some problems that an ice table won't help for, and we'll talk about that later in the hour. But almost all of these, it's going to be good to just organize yourself with an ice table. When the problem says the solubility, what does it mean, solubility? Benit?
It's the negative x change on the solid.
It's the change in the solid, that's right. The solubility is how much of that solid dissolves. And then it gets to equilibrium. And so the amount of this reactant that's not very soluble, that will dissolve, is the solubility. So this thing right here, and you do have to know this, that's what it means when it says solubility. My board is just off a little bit, so my writing's going to be messy. Okay? So if they're giving us that value, that means that this goes down by 4.8 times 10 to the negative fifth molarity. So if I start with 0 of each of these, and they go up by the amount that this goes down, these go down by, or I'm sorry, up by 4.8 times 10 to the negative fifth molarity, and 4.8 times 10 to the negative fifth molarity. So these are the equilibrium amounts. I don't know if I need to write them again. And so the question is, what is KSP? KSP equals that times that, both of them to the first power, and then divided just by 1 because that's not aqueous or aqueous or gas. So KSP equals 4.8 times 10 to the negative fifth squared. So we know how to do these kinds of equilibrium problems. Again, it's good to stay organized. Make the ice table. Know what it means to have a solubility, what that term is referring to, and it's referring to the amount that dissolves in the solid. And so the answer you get for this is, let's see, from my memory, I want to say it's 2.3 times 10 to the negative 9.
Oh, yeah.
Yes?
Just remember.
Just memorize. Yeah, I mean, this is close to 5. This is like 25 times 10 to the negative 10, which is 2.5, or 3 in this case. Times 10 to the different power on the 10. Okay. Anybody have any questions or comments about that? Yes, ma'am?
Then why do we say that, like, the solubility of the solid instead of, like, when we don't use it, or, like, when it's a solid and we don't use it in the...
Yeah, we don't even need to use it. In fact, the equilibrium line, again, I go back to just this undefined amount. But this does partially dissolve. Agreed? Because you're going to get some of that and some of that. That means some of that does break apart. And so that solid does, in some small amount, get changed. And so the change that is present, that is the solubility, is the amount that changes by. So that amount is related to those amounts, because as that goes down, those go up. So they're all related. Yes,
So the
now don't say anything bad about Nick just because he's not here.
no, I won't.
Okay.
For the solid, there's lines because like you can't take them away yourself, right?
Right, right. Yeah, the molarity of the solid is the undefined. Yep. Anybody else about that? Okay, good. Now, if we can move on to the next one, I'm going to ask you to try this one, and feel free to talk to others around you and kind of walk yourselves through this. I'm asking you the concentration of silver ion in a silver oxalate solution is 2.2 times 10 to the negative 4. Find KSP for silver oxalate. Try that. Coefficients aren't all ones this time, are they? No. So yeah, be on the lookout for non-one coefficients, because there'll be plenty. This is what's given in the problem. The equilibrium concentration of silver is given. That's what it's telling you. So if you know the equilibrium amount of silver, and you know that silver and oxalate started at 0, can you fill in the rest of the ice table?
Yes.
I think you can. Yeah. Yep.
So you divide that by 2, right?
Right. Since it's a 2-to-1 ratio, the amount of silver that's made is twice the amount of oxalate that's made. Yep. So where this goes up by 2.2 times 10 to the negative 4th, this goes up by 1.1 times 10 to the negative 4th. Half the amount. Yeah. So we have now the equilibrium concentrations. And we're asked for the KSP. It looks like it's pretty easy from here.
So you square 2.2.
Why?
Mm-hmm.
Why isn't X 2.2?
Why isn't X what?
2.2 times 10 to the negative 4. Why is it 1?
Because this is going to go down.
But, oh, okay.
This goes down by some amount. The problem tells us this right here. So since that's a 2-to-1 ratio, the X value would be 1.1 times 10 to the negative 4th. And then the amount that goes down, double that, that's how much AG goes up.
And the gas.
What's that?
Yeah, no.
About squaring this, yes you do.
Yeah, you do.
Yep. So go ahead, somebody else?
Yeah, can we just with like the C2O4 as 2.2 and
No, because look at what the problem says. The concentration of silver is that.
oh
Don't double it, just because there's a 2 in front of it. The problem it's telling us what this number is. So you have to just write it down.
that
It's,
was the concentration of the solid.
that's not what it says. The concentration of Ag plus 1. That's that.
Thank you.
It doesn't say how much of the solid dissolves. It says what that concentration is, so we have to go with that. Okay? So that would have been minus 1.1 times 10 to the negative 4. We don't need that at all, though, because all it's asking for is what the KSP value is. And that's equal to the silver squared times the oxalate to the first, like that. Yeah, 5.3 times 10 to the negative 12.
Hi,
Hi.
is Anna Zhang in here?
Yes.
I think I just heard for a second.
Yep, sure can. Miss Anna? Okay, that's 5.3 times 10 to the negative 12. Questions about this?
I know I can do math.
The problem did not tell you the solubility of this, so you have to double stuff. It told you, it gave us this, that was given. So we had to get everything else from that term. Anything? Okay, ready for another one? All right, here's another question. The KSP for silver sulfate, Ag2SO4, is 1.2 times 10 to the negative fifth. What is the solubility of silver sulfate then in water? We talked about what solubility is. It's this. We want to find that. That's going to dissolve some amount. It's going to go down by X. And this is just in water, so those start at 0. And if that goes down by X, those go up. That by 2X and that by X. Yeah. So our concentrations at equilibrium go into the K value. You're given the K value. So are we all together on this? Not too bad of a problem.
Sure.
Do the math on this one.
Oh wait.
So all you have to do is solve for X. The box tells us what we want to try to find. We're trying to find this thing right here.
Would you,
What is the solubility?
But we
Would
don't
you-
use the X on the left side. So we just
Right. Yep. But when you solve for X, that's going to be the answer.
would you divide by 4 and cube root it?
Yeah.
Oh, I'm actually understanding.
Looks like that. That right side turns out to be 4x cubed. And so solve for X.
I think I got something weird.
Do you not have
It's chemistry.
Like 1.4 times.
Yeah. Seems
Yeah, that's right. What's weird about that?
That's one of the biggest.
So 0.014 is our solubility.
it was
And I should have a molarity sign on there.
We don't usually see such big numbers in chemistry anymore, do we?
Not with solubility and concentration, no, no. Anna?
in the questions, for some of the questions, it was like this number, like plus x to like the third, and then they just neglect that. Oh yeah, just the. I was so confused at first. I was like, what is this? And then
Because I was doing the quadratic
Um,
formula and like
yeah,
expanding.
and like x is cubed, and I was like, yeah. And I was like, numbers of the x cubed to the cube.